Okay, sorry for the delay. We are starting. There are other people arriving. So let me just tell you a few things about how works these virtual seminars. First of all, welcome to this series, virtual series of complex system. The two seminars of today will be recorded, so please turn the camera off if you don't want to be recorded. Very few words before starting. Thanks, first of all, to the speakers to be here. I will introduce them in a sec. And thanks to all of you to be with us and to spend this afternoon to discuss about science. So the idea of this series is to put together different expertise and to discuss hot topics from different point of view. This is the spirit of the Center of Complexity and Biosystem. The organizer is me. I'm Caterina Laporta. I am involved in biomedical research. And with me there is Stefano Zapperi, a theoretical physicist, and Alessandra Micheletti, a mathematician, also involved in social science. So, complex system, the Center for Complexity and Biosystem is in Milan. I try to move, okay, I have a lot of people to admit. So we are located in Milan, as you know, the heart of the pandemic in Italy. Before introducing the speakers, let me tell you a few, little notes, practical information. So the seminars will be held every 2 weeks, and we have already the panel full till December. But please, if you want to send us proposal for the new year, is really welcome. Each seminar is about 40-45 minutes, and in this case, the discussion will be together since the two seminars are related closely. If you have questions, please post on the chat of Zoom or YouTube, and me, Alessandra, or Stefano will read the questions at the end of the seminar during the discussion panel. The next seminars will be 23 September at 4 p.m. Milan time, and we will have Francisco Rodriguez from University of São Paulo, Brazil, and Asaf Zaritsky, Ben Gurion University of Negev, Israel. So today we have we talk about COVID-19 from two different perspectives. Our first speaker is Andrea Crisanti. He's director of the Department of Molecular Medicine and of Laboratory of Virology and Macrobiology at the Hospital University of Padua, Italy. He recently returned to Italy from Imperial College London, where he is professor of molecular parasitology, currently on leave. He became famous for the study of Voioganeo, a pilot study of great importance of the first outbreak of COVID-19 in Italy. Work that he published on Nature. And the other speaker is Yamir Moreno. He's director of the Institute of Biocomputational and Physics of Complex System. He's the head of the Complex System and Network Lab and professor of physics at the Department of Theoretical Physics of the Faculty of Science in the University of Saragossa. He's an expert on disease dynamics, diffusion processes, mathematical biology, nonlinear dynamics processes, and the structure and dynamic of complex systems. His talk will be on data-driven modeling of COVID-19 pandemic, a recent paper that he published on Nature Human Behavior. I leave the floor to the first speaker, Andrea Crisanti. Please.
Thank you very much for the invitation. Now the first challenge is to add the presentation. Okay, which I should be able to do it. 1 second.
Let's just go on the share screen.
Let me see if this is the right one.
Perfect.
Okay. So let me load the presentation. Can you see? Okay. So in principle, this presentation aims at summarize the findings that we obtain in VO as well as to add new data and some modeling that somehow provides a more complete picture. So let me start first of all with the study setting. Though for those who are not familiar with Italian Northeast geography, is a very, very small municipality of about 3,000 residents. Their main occupation is agriculture, and they is really in the heartland of wine production of Northeast Italy. On the night of the 22nd of February, a resident of Vaux died in the hospital of Schiavonia, which is the local hospital there, of interstitial pulmonitis. He was later diagnosed with COVID-19, and this led to the lockdown of the Vaux, and at the same time, the local authority ordered that everybody in the municipality of Vaux had to be tested with swab for coronavirus detection. This created really a unique epidemiological setting, and we asked the local authority to repeat this swab sampling a 9-day distance in order to understand better the transmission dynamics of the epidemics, to assess the impact of the lockdown, and eventually also to model the spread of the virus. One second, because I have a small problem with this. Okay. Now, the panel in B is a representation of the epidemiological survey that we conducted in the municipality of Vaux. There are about 3,275 residents. On the first sampling, 2,800 were tested, 2,739 were negative, and 73 turned out to be positive. This accounts for about 2.6% of the population. So this means that at the time we had the first person hospitalized, already the virus has spread to infect about 2.6% of the population. This is a piece of information that was dramatically underestimated. It was under the eye of everybody, but unfortunately, the Italian political authority underestimated this data, and they spent about 10 days in minimizing the problem. Now, on the second survey, we had a dropout of about 600 people, 557 negative and 8 positive. And we recruited about 90 new people. And this is the outcome of the second testing. There were 2,300 people, 29 positive and 2,300 negative. And again, there are some difference, of course, because some people recover from the disease, and we have some new cases. Now, on panel C, you have a timeline of this survey. In red, you have the first survey, and in principle, and is the date of the lockdown and the date of the second survey. So in principle, between the first survey and the second survey, there are about 10 days. Now, this is the age distribution of the subject tested. So, as you see, actually, I should mention that the population of Vaux is not a good sample of the Italian population, because we we have checked with the Italian demographic registry, and is a bit skewed towards older class ages. But the reason why we show this slide is to show that there is no difference or big statistical difference between the first and the second survey that could have introduced a bias in the data. Also because we know that the disease affect differentially people of different ages. So, and as you can see also, the median and the whisker plot do not differ dramatically in the two groups. So they could be compared. Now, this is a summary of the statistics of the SARS-CoV-2 prevalence in the first and second survey. So in the first survey, 2.6% of the population were positive. In the second survey, this dropped to 1.2%. Now, and on the B panel, you see this represented in number. So you have about 73 in the first survey, about 29 in the second survey. And the most interesting thing that is in the second survey, there are 8 new cases. And the difference between this one and this one is because some people recovered meanwhile. Now, and it's interesting also to see who recovered. Now, this is an analysis of individuals positive for the virus, the first and second survey stratified by sex age group. And you can see there is a little higher prevalence for male than female, but this is not statistically significant. However, when you analyze this data from the second survey, you see that there is a statistical difference. And the reason is that the women tend to recover much quicker than male. So in principle now, this is the age distribution of individuals that were positive for SARS-CoV-2 in the first survey. And it's interesting that, for example, in the age class between 0 to 10, we analyzed 217 individuals, and not a single one was positive at the swab. And we see that there is a progressive increase in the number of positive individuals towards older age. Now, if you look at the second survey, we see that the number decrease, of course, because many individuals recover, and particularly in the older age group, between, let's say, 51 to 70, the difference between the first survey and the second survey is that a lot of women recovered. So particularly in the older age group, the women recover much quicker than male. And these are the new cases. And again, the new cases are all clustered in older age group, and we see only one in a younger age group. This is again is a different way to represent this data. Now this is the first survey, this is the second survey. The difference in the prevalence for individual age group represent the people that recovered from the disease in this span of 10 days. Then each individual was interviewed for the presence of symptoms. We investigated whether they have fever, cough, headache, sore throat, discomfort, conjunctivitis, diarrhea, and lack of anorexia, lack of or disturb in the smell and taste. Now, what we found, I must say that this individual, according to the presence of the symptoms, we could divide this individually in 3 classes. They were either symptomatic at the time of samples. We found about 46% of people were symptomatic. We found 10 individuals which were not symptomatic at the time of the sampling, but later on they developed some symptoms, and we classified them as pre-symptomatic. Then there were 29 individuals that were completely asymptomatic at the time of sampling and remain completely symptomatic later on. They never develop any symptoms. And this is again the same distribution at the second survey. And obviously, at the second survey, you see a dramatic drop in the pre-symptomatic, because after a few days, this individual develop symptoms. So you shouldn't be surprised that you have a drop from 10 to 1 in this particular class of the individuals. The difference between this and this is that they recover. The difference between this and this, that most of them develop symptoms. So now, if we want to move the second analysis we carried out on this individual, we want to investigate whether there was a difference in the virus copy number. So what we did, we analyzed, we compare the copy number as expressed in a number. This is a logarithmic scale of a number of cycles for 2 genes. So the RT-PCR generate a signal which is dependent on the cycle and the amplification cycle, and the lower is the number of cycles that you need to see a signal, the higher is the viral load. And in principle, this is for 2 genes, what is called gene E and what is called gene RDP. And as you can see, this is the distribution that we see for asymptomatic and symptomatic in orange. For the 2 genes, we couldn't see any difference here. So in principle, we could not detect a major difference in the viral load when comparing asymptomatic and symptomatic individuals. Then we also, for some of these individuals, we were lucky to have several determinations on different days. And as you can see, this shows that, again, the copy number, for example, for these individuals at the beginning of the infection, then progressively goes down. And this is irrespectively whether they were symptomatic or asymptomatic or pre-symptomatic. So in principle, the symptoms, the presence or absence of symptoms do not predict for viral load level and for the time course of the decrease of the viral load. Then we did some contact tracing, because on the new cases, as I mentioned to you, we had new cases. We had 8 new cases, and between the first and the second survey, so we investigated very closely their contacts. And so we have now 3 individuals with symptoms, and we have 4 individuals which were asymptomatics. And so we were able, for most of them, to identify the source of infection. And for example, for this patient 2, the only source of infection could be contact with other 4 individuals on a family gathering, and which none of them have any, all of them had none of them had any symptoms. Then we had patient 3, for example, we could identify the source of infection with 2 individuals which were symptomatic. And again, for example, patient without symptoms, we could identify the source of contact with 1 person that had no symptoms, and which was a contact, and which was a cohabitant, and the same for patient 8. So this is we believe that this was very important, because it showed that a symptomatic individual not only have the same viral load of symptomatic individual, the same time course of the viral load, but they also are able to transmit. And I think this was an observation done at the beginning of March, but now everybody agrees that the asymptomatic individuals are a major problem for the control of this, the spread of the virus. And I'm sure in every country in Europe now we see that the majority of asymptomatic individuals. I mentioned to you at the beginning that there were 217 children, and none of them was positive at the swab. And interestingly, 10 of these children shared household with positive cohabitant that spread the infection to nearly all the family except the children. There were 10 in the first survey and 3 in the second survey. We also have another 2 children which had contact with positive relatives but no cohabitant, and again they were negative to the swab. So in principle the children were negative, remain negative, not because they didn't have contact with infected individuals which were able to transmit, but they were negative, and I will show you later they also remain negative at serological tests, and we really do not understand why the children of age between 1 to 10 are resistant to the infection. Then we also ask another question, which is what is the probability of a person sharing a household with an infected person to become infected with respect to somebody who share household with non-infected people. And this was done with these new cases, and we found that individuals which share a household with infected individuals have about 80-fold higher probability of becoming infected than individuals which in principle do not share household with infected individuals. And this also helped us to explain the time course of the epidemic in Italy after the lockdown. The number of cases decreases much slower than anticipated, because there was a dramatic contribution of household transmission as well as community transmission, particularly in elderly home. Then with the help of our friend at the Imperial College, and this is data produced by Ilaria Dorigat in the laboratory of Neil Ferguson. So you forgive me if I'm not so good in explaining this data. So we prepare attempt to develop a mathematical model that could fit point of prevalence of data observed in the first and second survey. So this initial model included a susceptible individual like S, E for exposed individual. Then we have infected asymptomatic, infected asymptomatic. Then we have individual that are positive and infectious, asymptomatic and asymptomatic. And then we have individual which have recovered. Now, if you develop this model and you assume a different level of R naught, 2.1, 2.4, and 2.7, and different time length of infectiousness, which is 1 divided by sigma. Now you see that this model intercepts the prevalence observed data at an R naught 2.7 and sigma 1 over sigma at around 4 and 6. Then we also want to understand whether the presence of the pre-symptomatic individual could somehow change this analysis, or whether they had an impact in the model. So what we did, we then developed a more complex model which accounted for the presence of asymptomatic individual, symptomatic individual, and pre-symptomatic individual. And again, this model includes susceptible individual, infected with undetected viremia, so non-infectious, then asymptomatic detected viremia, which are infectious. Then we have symptomatic detectable viremia infectious, symptomatic detectable viremia non-infectious, and again, these are the asymptomatic. And then finally, we have recovered undetectable viremia. So in principle, these individuals here can either become asymptomatic or symptomatic. So in principle, these are the so-called pre-symptomatic. Now, again, this is again the same modeling for different level of a ratio 1 to sigma that in principle represent the time when individuals are infectious, and different level of are not. And again, the best assumption are at this one, 1 to sigma equals to 8, and are not around 2.7. So around this value, the model intercept the observed prevalence. Now, this model also tells us another interesting thing, that probably the first infected person entered the municipality of Vo towards the last week of January or the beginning of February. So in principle, the virus spread undetected for about 4 weeks in the municipality of Vo before generating severe disease. We still don't know why this happened. Then we carried out also seroprevalence on all the inhabitants of Vo. And this is a summary of the results. So in principle, we have a subject positive to at least one swab, which are 65, and 76% are also positive to the serology. Now, at that time, the serology was carried out only with one technology, which is diazorin. Now we extend the analysis of the whole population with the 3 technology, which is diazorin, Abbott, and Roche. I don't have yet the time to explain to you the difference what you see with different technology. But the interesting thing is that the serological analysis also identify individuals which were negative at the swab. So we have 63 individuals, which are here at different class ages, which are positive. So they have antibody against the virus, but they are negative at the swab. So in principle, these are individuals which at the time when we carry out the swab, they had already recovered from the disease and then nevertheless developed antibody. Then we looked at the different, if there was a difference between symptoms and seroconversion. Sorry, here it's I need to do something because otherwise, unfortunately, I don't know why this is. I lose the legend. So in principle, this is the IgG titer in subject positive to swab testing in asymptomatic, symptomatic, and in principle, we don't see much of statistical difference in the distribution of the IgG titer. And neither we see when we see subject positive put to both serology and swab. But we see a difference when we look at asymptomatic and symptomatic individuals, when we look at individuals which are IgG positive, but they were negative for swab testing. So in principle, these are individuals which become infected before the first survey. So this in principle means that this individual became infected earlier. And this is again, particularly, this is independent of swab, but this is when you go for negative swab. So all these 56 individuals were infected before the first sampling. And interesting, their antibody level is much lower than the rest. And this tells us that the antibody response against this particular antigen is not long-lasting. And this is also now being confirmed by other studies. Then I come to my last slide. So this again is a summary of the model that intercepted the prevalence data. And this is an analysis that in principle tells us what would have happened if the first swab testing had not been carried out and positive individuals have not been put in isolation. So in principle, this is the first swab testing. This is the this is the supposed introduction of the virus in the community, and this is the first swab testing. At the time, all the positive individuals were put in isolation. So in principle, this shows that the incidence would have increased dramatically daily, and in principle, in 4 weeks, probably 75% of the population would have become positive if a lockdown and testing measure had not been implemented. This is the difference with the measure. So in principle, the lockdown reduced the RT by 98%, and in principle spared at least 100 deaths in the population overall. There is also another interesting aspect that validates the model, is that the area underneath the supposed beginning of the infection and the 24th of March indicates that there were at least 140 individuals infected in the municipality of Bo. And at the time, we didn't have any data about the serological tests, but now we have it. And we know that there are 63 individuals which are positive for the antibody and negative for the swab. So this means they have been infected before the first swab survey was carried out. Plus, we have the 73 individuals which were swab positive. So altogether, now this makes 136 individuals that had been infected by the 24th of February, which is very, very close to the model prediction. So I think I stop here. I think it was about 40 minutes. And I leave to the second speaker.
Okay, thank you very much to Professor Crisanti. Now I will introduce the next speaker, Professor Yamir Moreno. As we said, as Caterina explained before, I'm Stefano Zapperi, for those who didn't see me. As Caterina said before, we'll have all the questions at the end, and you can start to put them on the chat if you want, then we'll read them to the speakers, to either of the two speakers. We can also say to whom you want to answer, ask the question, or maybe the question can be to both speakers. So without further ado, I leave the floor to Yamir Moreno, and with the second talk of the session.
Thank you very much, Stefano. Let me just share my screen with the presentation. Okay, so here we go. So I will be, thank you also, Professor Crisanti, for your nice talk. Mine would be complementary to yours, I think, because I would be talking about modeling COVID-19. So it's let's say the more mathematical part of what has been doing in this period. So I will introduce the topic of disease modeling, and then at the end I will go to discuss some aspects of this COVID-19. But let me just first start by, this is a little bit outdated. This is on July 17, but you already know that the disease was hitting hard. Several parts of the world, is actually worldwide already, and that this there were no signs of that the, let's say that the situation was becoming better. At that time, I specifically took this date because at that time we were discussing whether to lift the restrictions in several countries or not. And so our modeling work was trying to provide answer to that sort of question. And the issue is that without any restrictions on mobility and trying to put some hurdles to the transmissibility of the virus, it wouldn't have been possible to, let's say, start to decrease the number of infected cases, at least in Europe, where it appeared to be under control until a few weeks ago that it started to increase again in several countries. Of course, this COVID-19 is not the only global disease that we have faced in the last, I would say, 20 years. This is from 1998. And as you have seen, there have been several, between quotation, warnings that a big pandemic will come up at some point. And this is COVID-19, but we have several cases that were already a threat for public health, like, you know, the H1N1, the SARS, the MERS, Zika, Ebola, etc. So all these diseases were already showing up, and this made it possible for people like me and other groups to start thinking on how to model the spread of these sort of global pandemics or global diseases. So how we can take into account the fact that we have changed our mobility patterns, that we have changed our interaction patterns, that cities are becoming denser and denser, and that the transportation means are faster, which means that we have less time to react and to put in place some measures to counter attack the pandemic, etc. So all these kind of questions, we started to think about it. Few of my colleagues and co-authors actually took this very seriously, like Alessandro Spignani, who introduced it quite some years ago, the notion of, or if you want, was one of the first that introduced networks and the study of interactions into models of disease spread. So when we started to think about this, there are a few questions that you made yourself to try to answer the problem of how to model this sort of disease. And there are a few things that you need to include in the model, whatever is your model and whatever is the disease. So the first one is how the disease is transmitted. So if it is airborne disease, if it is vector-borne disease, etc. The second one is what are the disease stages, what is the natural history of the disease, whether you have asymptomatic transmission, whether you have pre-symptomatic transmission, if you have latency times, whether these latency times are short like for flu, or if they are of the order of years like for tuberculosis, for example, etc. So how the disease is spreads between people. In this case, we are talking about human disease, so we need to also characterize how people interact to know how the disease is spread, because at the end of the day, we are the carriers of the disease. So if we move to a new place, we take the disease with us. So we need to know how we move and how we interact with others, how we mix socially in a sense. And finally, this is also a big issue when you are modeling these sort of diseases, is the fact that you are modeling a system that is also able to change and to, let's say, once you provide feedback and you predict the course of the disease, these are people, so they can get that information and adjust their behavior. So this behavior induce further change in the system that you haven't taken into account when you did the prediction. So you have to continuously update your prediction as a function of how people behave and how people change their patterns. And for example, if they adore mass reading, that means that the transmissibility is reduced, etc. So all these factors have to be taken into account. And by the way, the last one is one of the hardest to take into account because we humans are not the molecules of an ideal gas. So we cannot think of a human like a rational subject that will react to the presence of the disease in the same way, whatever this place is, whatever the country and the condition. We have a lot of heterogeneities to take into account, and we have seen this with this disease. It's not the same, the sort of reaction that, for example, has been enforced in countries like China with the sort of measures that have been enforced in Europe or even in the US. So in this sense, there are a lot of plethora of behavioral change that you have to take into account when you make the prediction, and this have to be taken into account in your model. Mathematically, the framework is very simple. Unfortunately, the most basic models that we have, and on the other hand, they are the mass studies, are not very useful for COVID-19 because COVID-19, the natural history of the disease, is a little bit more complex than a simple susceptible infected susceptible model. It's more close to what we call susceptible infective removed model, in the sense that you are susceptible, then you get the infections, and then you either recover or you die, and then you don't play any role furthermore in the dynamics of the disease. But between these susceptible and infected, there are a lot of compartments that are also important for the dynamics of the disease, and also between the infection and the removal state, there are also a lot of compartments that are as well very important for the disease. You can go into severe disease, you can need mechanical ventilation, etc. And this is very important in terms of the public health implications. It's not only how you model the disease, but also what are the implications for the public health. By the way, this is just a parenthesis here. There is, it's also important to, I think it's important to say that it is not the same to do epidemiology than do public health. So epidemiologists normally do what I am explaining you, and you can be a mathematician or training in mathematics or in physics or even in computational computer simulations, etc. But if public health is more than that. So public health is what is the branch of the health sciences that take into account the feedback of a computational epidemiologist, and then integrate a lot of information with a lot of SIMs and make a decision, or do a recommendation at a higher level. That's just a parenthesis, because sometimes we think that we can speak about what have to be done when there are a lot of aspects. So it's a multi variable state problem in which you have to take into account a lot of things before you speak out in terms of recommendations. So we are limiting ourselves to study the disease spreading from the more epidemiological point of view. And of course, this is one possible, let's say, ingredient in any decision making from the point of view of public health. So our model for COVID then is a little bit more complex than this SIR. I will explain it a little bit more in details afterwards, but for the time being, this is the natural history that we will be considering in the when we study the more detailed model. Essentially, you have, as Professor Crisanti was mentioning, you have different stages of susceptibility. Then you have different stages in which you are incubating the disease or the virus, and then you become symptomatic or asymptomatic, etc. The more interesting thing is that the rate, the probability that the susceptible catch the disease depends also on who transmits the disease. It has been reported that these rates are different if you get the disease from an infectious asymptomatic, an infectious symptomatic, or pre-symptomatic. And the hypothesis is that this has to do with the viral load that you are confronted with. And so in general, we use different rates for the when you analyze whether a susceptible in contact with any of these individuals goes to a latency state, that then it could be asymptomatic, and then you go to the branch of asymptomatics, or symptomatics that there have a pre-symptomatic state, and then the infectious symptomatics that could be directly to recover, you go to recover without the need of being hospitalized. If you are hospitalized, furthermore, we add the fact that you can be hospitalized or that you need ICU care, that is a more serious stage of the disease, in which you can also need mechanical ventilation, etc. And then it's a more severe. This is where the problem is actually in COVID, because if the disease were like this in these two branches, infectious asymptomatic or infectious symptomatics, that wouldn't be a huge problem if given the mortality rates that it has at the moment. The problem is that this here is where the infectious fatality rate increase a lot, because people start to experience the severe stage of the disease, and especially this puts a big pressure on the healthcare system, because you have to have enough beds to take care of these patients, or enough mechanical ventilators in case they need ICU care. So any measure that you take is aimed at trying to keep the level, the burden below what is your capacity at the public health or at the healthcare level. So this is one thing that we will take into account later. As all diseases, this COVID-19 also, we are not going to talk about it, but is the typical phase diagram for disease spreading. So you have that, you have a parameter that is the basic reproductive number. Is the basic reproductive number is less than 1, then this means that you have less than a secondary case, and that eventually the disease will not kick off, and then you are in the disease-free regime. If R naught is larger than 1, then that means that there would be a disease outbreak, and the macroscopic fraction of the population would be affected. So you will have more than 1 secondary case, and then eventually you can also enter into what is called this exponential growth phase, in which the number of newly infected individuals grows exponentially fast. These are not for a homogeneous population. Essentially, it depends only on the parameter of the disease. When there is a well-mixed population, etc. But obviously, we don't interact in a well-mixed population. We interact with networks. Not all of us interact with the same number of people. So this means that this reproductive number also depends on the number of people on the interaction pattern. Let's say network of interactions, and this is why it is important to study this spreading mechanism that I was referring to earlier, and understand how we move and how we interact with other people, because that will have an impact in the way in which the disease transmits between humans. From the more computational and data point of view, you have different approaches that you can follow. So one these are the two that we are going to explain later and that we are going to follow. The first one is to consider that you have a metapopulation system. This is in the top. I don't know if you see the arrow, but this I'm talking about the top left panel. So this is a metapopulation system in which you consider that the world in this case, or if you want to model at the country level, your country or whatever, is made up by different subpopulations. Within given subpopulations, you consider that there is now a structure for the population. So it's a well-mixed population. but the connections between the subpopulations allows you to study the spread of the disease geographically speaking. So for example, imagine that a given subpopulation is identified with a city or a small region in the country, and then the connections between these cities would be given by mobility connections between them. So by car, by train, plane if they are distant apart, etc. This is one way to model the spreading of the disease, and it's particularly suited when you want to model the spread of the disease at a very large scale. So you can have as many subpopulations as you want, and then at very large scale, you can study how it spreads by also studying the pattern of connections between these different regions. I will present a couple of works that have to do with this approach. And the other one, which is more suited for a local study, when you study, for example, the transmission dynamics within a city or within a given small region, is an agent-based model in which you have to model the dynamics of each individual in the population, and you also couple to this the dynamics of the disease. So in our case, we are going to divide the population, that could be one of these subpopulations that I was talking before, in 4 layers, 3 to 4 layers, depending on the quality and amount of data that you have. So there is one layer that is what we call the school layers, in which you essentially have all the interactions that takes place at the schools, kids or children, and also college, it's also university, etc. Then you have the workplace, that is when people go to work and they spend some time there. So these are interactions that take place at workplaces. Then you have the household layer, that is very important also because a lot of interaction take place at the household layers, and actually you spend half of your day, maybe even more at your home. So you interact with your family, etc. at your place. And then what we call the community layer, which is a layer in which random interactions take place. So essentially this is the layer where you encode interactions that take place, for example, in public transportation, or if you go to a shopping to do some shopping, then this is, or a theater, or you know, a mass gathering event, or restaurants, bars, etc. So this is another layer in which we let's say put all these places, and this is also a store of a lot of contacts that are produced during the day. So I will first, maybe I will just mention this, that what we are going to do now is first to study the early stage of the disease, and for that we will study how it spread in China and in Spain at the very beginning, and then we are going to study how to what kind of measures we can take to reduce the burden of the disease and to let's say go back to this sort of new normality safely. What can we do not to, I mean, to put a cut or a barrier to the spreading of the disease. And this is because from an epidemiological point of view, the only way that you have to stop the spreading of the disease is when you population is immune and immune to the spreading of the disease. And this can be achieved by only in 2 different ways. One is that you have a vaccine, and then you vaccinate your population, and then that confers immunity. And the other one is that your people in the population get sick and they recover, and they get this sort of natural immunity by recovering from the disease. Of course, if you have vaccination, that's okay. You don't have to vaccinate all the population. It is now in epidemiology this concept of herd immunity, in which it means that if you protect a given fraction of your population that is smaller than the total number of individuals that you have in the population, that is enough to stop the spreading of the disease. And the math is very simple. If you consider a homogeneous population, you can relate the R naught with the fraction of the population that you have to vaccinate to achieve that. Alternatively, you can also assume that, okay, I'm not vaccinating the population, I'm just allowing the people in my population to get infected and recover, and the same fraction of individuals will confer herd immunity. For COVID-19, this second path is not possible because, as we were discussing, there's a lot of people that will end up in the hospital, and the transmission is so fast and so efficiently that the number of individuals that will get the infection will be huge in a very short time window, and that will saturate the whole healthcare system and will induce or will lead to unnecessary death of people that will not die if you were able to distribute that amount of people, infected people, over longer times. So this is just to mention that even if we are not now in the condition to vaccinate people, and that we can now go for complete immunity by allowing people to freely get the infection and recovering, we cannot forget that as time goes on, more people are getting the infections, and at some point we will be close to this herd immunity, which this seems to be very high. This is for measles, but has been calculated for COVID-19 around 60 or 2/3 of the population. But this is considering that the population is well mixed. Actually, if you take into account that we interact in networks, etc., the level of herd immunity that you need is smaller, and there is one paper in Science that suggests that this is around 43%. I believe personally that this could be even lower than this 43%. Anyway, it was just a side note. Let me just discuss what we have done using metapopulation and agent-based models, and also pluging data into the model. The first one is about the early stage of the disease. So what you will see here is a simulation of the movement of in China around the dates. You see here the dates. This is January 24, January 25th, etc. So the issue here was that in China, they have this new, they call Spring Festival. And this Spring Festival is like our New Year. So they start to move huge. It's a huge migration. So for you to have an idea, it is estimated that around 3 billion people move during time window of a couple of weeks. 3 billion. So we are talking about that, like half the world population move in those 15 days. So that's the estimation. So you can guess that there is, it's perfect condition for, that's the perfect storm for a virus to transmit with 3 billion people moving around. So what we did was to get some data about mobility in China before and after the Spring Festival. I will explain this in 2019 and 2020. So this is 2019, where there were no problems with any virus or any transmission. So this was kind of free movement. So you see that the pattern, the mobility pattern, is characterized by two peaks. One that takes place around 1 to 2 weeks before the Spring Festival. And these are people that start traveling and go on holidays and go to see their parents or go to see relatives, etc. So there is a peak around that. Precisely around the Spring Festival, there is the minimum mobility because everyone is where they wanted to spend these dates with family, etc. And then after the Spring Festival, there is a second wave of people that go. What happened in 2020 is that with this COVID-19, there were travel restrictions, and actually it was imposed this sort of lockdown in which people could not move, but already the first wave had taken place. So that means that from the point of view of stopping the spreading of the disease, it was effective as it cut down the second wave, it avoided the second wave, but not as effective as it could have been if it were implemented like 2 weeks before. Because when it was implemented, it already had, a lot of people have already moved at that time because you already had this first wave that we observed in 2019 and 2020. So what we did was to simulate the spreading of the disease, assuming that the mobility is like 2019 or that the mobility was like it was actually in 2020. I don't have the results here, but the results show that actually this explains the difference between the incidence in different regions. So it explains why it didn't grow up after you impose the travel restriction, because you don't have this second wave. But the first one was important enough as the virus to go out of Wuhan and start spreading to other parts of China, and from other parts of China also to the southeast and then to Europe. The second analysis that we did was for Spain. This is also early stage of the disease. In this case, what we had was access to data that it's about mobility within Spain, but it was disaggregated by transportation means, which is quite nice because it allows you to explore different measures as a function of whether you shoot down one transportation mean or the other. So in this scenario, what we did was the following. We had data about internal mobility within Spain. So this, for example, panel C summarize all the data. So here we have all mobility. So this is only airplane, coach, that means buses, cars, particular cars, chips, and trains. So all of this was there. And you also have importation risk from different countries that you can also plug into your model if you want. So this was data that we have in normal conditions, so there were no restrictions. Now we have also data about how this mobility pattern was changed as a result of the measures that we're taking. But for the sake of the simulations that we were interested to do, what we needed was pre-COVID. So what was the mobility pre-COVID? And this was this. So here what we did was to simplify the epidemiological model. So we are only using a susceptible, exposed, infective, removed model. And we did an exercise that was that was intended to see how the disease spreads geographically in Spain. As you can see here, let me go back, you see that this is the central point here, this is Madrid. And then you see here in Spain, communication have a very centralized pattern. You see that either if you go by airplane, coach, or well, car or trains, most of the communication go through Madrid. So that means that if I am here, for example, that this is Zaragoza, and I go by train, I go from, I want to go to Seville, that is around here, I have to go to Madrid and then to Seville, but there is no direct connection like here, like this, from here to here. So I have to do like this, to go from here to here, sorry. And the same by car, if you have the highways, normally you go like this. So it's very central. That means that one hypothesis was, okay, if this is, if the mobility patterns play any role, if I do a simulation of the disease that is seated in Madrid and I let the disease evolve, this should be distributed homogeneously to the whole country because Madrid is like the hub, it's the central one. While if I start the disease in any other place that is not as central as Madrid, but is important enough, like Barcelona, for example, I should notice the difference due to the mobility patterns in Spain. And actually, this is the case. If you see the disease in Madrid, this is the top panel. After 25 days, you see that this is Madrid and only the very surrounding provinces. And then if you go up to 50 days, you see that the incidence is higher in Madrid, but essentially all Spain have already experienced the COVID outbreak. If you instead start in Barcelona, you see that after 25 days, so locally, still is locally in Catalonia, but then after 50 days, you see that the, let's say, northeast part of Spain is the only one that is more at risk, and the west part of Spain, that is close to Portugal, is still COVID-free, let's say. Of course, if you wait long enough, you will end up with people also getting infected in this region. But this is important if you are thinking about contention and about mitigation measures, because that essentially buys you time, and this is very important for the disease, to have as much time as possible to evaluate possible measures, etc. So this is one first result, and the second one that we did was to see what happens if we implement different measures. At that time, the measures that were discussed were reducing mobility and increasing detection, etc. So this is the summary of the results. As you can see, this is in all cases. This is red means that you do nothing. So this is the reference case. This is the case what you will get if you do nothing. As you can see, if you shoot down the different transportation modes, so for example, airplane means that you shoot down this mobility layer, so no airplane transportation or coach or car, etc., you get no reduction in the outbreak size. Not even a 90% global reduction. So that means taking down 90% of each of these transportation modes. The effect is slight, it's a little bit, it's small but noticeable when you measure days to the peak. So you see the disease, and then you measure how long it takes for the disease to peak, and then you see that 90% reduction improved with respect to doing nothing, and also a movement by particular cars. Any other measure is completely useless from the point of view of the mobility to reduce the time to the peak and essentially earn a little bit more of time. The other measures that we were evaluating at that time are the measures that are directed to either could the transmission change, so you identify what are the symptomatics and then you isolate them, or reducing the transmissibility by using mass, etc. So in the middle panels, you can see what happens when you isolate, you detect the symptomatic, and then you isolate the symptomatic, so you could the transmission change, and then the red again is doing nothing, so no isolation, and then these two, 1.5 and 1 means isolation within 2 days of being detected, 1.5 and 1 day of being detected or being infected. So this is, you see that depending also on the incidence level, the measures are more or less effective. Of course, that means that the sooner you detect cases, the more is the reduction that you get in both the outbreak size and the time to the peaks. That is not represented here, but the results are similar. You can, of course, you can say, oh, but I cannot detect everyone. So let's suppose that you only detect a given fraction of the infected in your population. And let's suppose that this was actually a problem at the very beginning in Spain, and that partially explained why we went into problems so quick. Because in Spain, the case definition was completely wrong in the sense that only people that were, that had some link with China or that were in contact with someone that had some link with China were tested at that point, when there was already community transmission. So that was a problem, that were a lot of people that even with symptoms, they were not tested because they were told that they had not connection with China, etc., and they were not tested. So, and of course, they also contributed to the propagation of the disease. So if you assume that the detection efficiency or efficacy was 30, 40, 50, or 60%, you see that also this implies that the more people you detect, of course, the more reduction you achieve in the outbreak size, in the size of the outbreak. And finally, there's a transmissibility reduction that could be by social distancing or wearing masks, etc. So you assume that the reproductive number is reduced by 10, 30, 50, or 60%, and then you see that also you get reductions both in the outbreak size also, and in this case, the days to the peak increase because then the disease is spread out more in time. So this is the reference. If you want more details, let me just go to the last part of my talk, which is the model that we developed in collaboration with Esteban Moro from the University Carlos III in Madrid, and the group of Alessandro Vespignani and other in Boston, and other colleagues like Natalie Dean, etc., that are also, they are epidemiologists. So in this case, what we had was data about the geopositioning of individuals. So there was a company, Quebec, that they collected data for good. So they were used to use this data to analyze inequalities, etc. With this pandemic, it turns out that this data was very valuable because with this data, you are able to actually build the network of interactions of the individuals in your population. So essentially what you have is the location of the individual at any given time. So if there are two individuals that are close enough and in a sufficient and interacting for a sufficient long time, you consider that this is a potential contact for the transmission of the disease. So, and then you can, if you have the geolocalization, you know where this contact took place at the household or a workplace or at the community layer or even at the school. So we built the agent Bayesian model with around 2% of the Boston population. It's 85,000 individuals, 60,000 something adults, and 20,000 something children. They were located in 3 layers: a school layer that, as we will see, play almost no role in our simulation because school were closed. Workplace plus community, which we integrated here, both the workplace and the community, and the household layers. These are the maps of, this is the map of the metropolitan area of Boston, and you can see the population distribution. This is the children, and these are the adult population. And we use the same model that I mentioned before. So this is the describe the natural history of the disease. You're susceptible. You can get the disease from infectious symptomatics, or pre-symptomatics individuals at different rates. And then you can experience one of these branches, the asymptomatic or the symptomatic one. And eventually you can also end up in the hospital or in the ICU. So just to put it in perspective, what we were explaining before was using these meta-population models in which we were considered subpopulations that were the provinces of Spain. And now we are kind of zooming out one of these places and consider that the structure of this place is that. This is a good approximation because the period in which we are going to study these dynamics is the period in which the mobility was pretty much reduced. So you can safely consider that this population in Boston is close because there are not influx of people coming from other places. The mobility is restricted, so it's actually in lockdown for a long period. So the population is constant within that time window. If you want to study this in a general scenario, you will need to also couple this subpopulation with influx of people coming from other places that will also play a role in the transmission dynamics. But for now, we can consider that this population is like isolated and you study the internal dynamics there. These are some data about the structure of the contact networks. You see here in the baseline scenario. So when there is no restriction of mobility, you have this distribution by layers. So 78% of the contacts take place normally in the community, in household 3.2, and the schools almost 20% of the contacts. Medium closure. So as you know, there was a period in which only the schools were closed, and also it was a reduction in essentially in community because there were some places that were closed, like church, museums, theaters, etc. Some restaurants remain open, others not, etc. But there was a huge reduction also in public transportation, etc. So actually it was 72% of drop in community, in the number of contacts in community. The schools were completely closed, so there was a 100% reduction. Of course, no reduction in household. And finally, there is the non-essential closure, that is the very strict lockdown, in which everything that is not essential remain closed for a given period of time. This means that that was a drop of 92% or almost 93% in community with respect to the baseline scenario, and the schools also remain closed. So these are the distribution of the contacts. This means that the average contacts here was around 60, here was 21, if I not remember wrongly, and this is around 6 or so, the average number of contacts of the people. So we analyzed the 3 scenarios, and I will finish with 2 slides. We analyzed it, 2 different scenarios for lifting the measures. But first, let's analyze what will happen, as Professor Crisanti did, if you don't take any measure. This corresponds to panels A, B, C. If you don't take any measure, this is the expected daily, the incidence per 1,000 people. And you see that there is a peak here around 12th or so of April. As Professor Crisanti reported, the expected number of people that will get the infection correspond to roughly 75% of the population. And this is the evolution of the reproductive number. It's a huge increase. And then when you pick this, well, actually it starts to decline. And when it peaks here, it corresponds to this, when it grows below 1, that means that it doesn't grow anymore, and then it starts to decrease. This is what you will expect in the baseline scenario, so you cannot allow for this, essentially because this will saturate all your healthcare system. 75% of the population getting the infection in about 2 to 4 weeks. That's too much for the system to handle. So you are constrained to think what to do. The first thing that was done was to impose a lockdown that essentially was at the beginning was soft, then it went into non-essential closure. So everything was closed except essential places. So you need to figure out how to get out of this, because you cannot remain in a closure forever, 6 months or 1 year until you get the vaccine and you are able to distribute and vaccinate your population. So you have to come up with a solution for that. And this is what we did. So we analyzed 2 scenarios, one in which after the lockdown that lasted 2 months, you first do a partial reopening, and then that means that you go to this second medium closure. So you go here, essentially you open workplaces, etc., but with some restriction and no mass gathering events, etc. So you don't allow for big concentration of people, etc. And then you do a total reopening without any testing or contact tracing, etc. And then you essentially get back to the previous situation. The incidence, the peak is not as high as it was before, but essentially you get into this population, like 60% of the population still is at risk. And then you see that there are a second wave here, also in the reproductive number, etc. So this is what you will expect in the second wave if you do nothing when you reopen the scene. So the problem is to avoid this situation. So the more the other solution is what we call lift, which is essentially after you do the non-essential closure, you do a partial reopening plus quarantine. So essentially you identify the symptomatic individuals, and then you also do some contact tracing. You trace the contacts of those individuals. This dotted line here represents the scenario in which you do testing and quarantine, but you do not do tracing. So you will see that again, this is smaller than this. Was around 14, and this is around 10, the incidence per 1,000 people. But still, this is too much, because this is still 50% of your population going into the path of infection. Though that's will saturate the healthcare systems. We will see next. So what you need to introduce, apart from testing and quarantining those that are positive when tested, you have to do also tracing. The most important part of here is that you don't need to do a South-East tracing. As we show in our model with 20–40% of tracing, so that means to identify two or if you want 1 out of 5 contacts or 2 out of 5, or that's already enough to reduce hugely the number of people infected per day. And you see that the incidence is here. Of course, you pay the cost that people are getting the infection very slowly, and then this makes that the disease last for longer than before, because you see that this is already plateau here, but here is still increasing. But if you keep doing this, you avoid this huge peak here, and then you keep a level of incidence that is something that the healthcare system can absorb. Actually, you can measure this. This is the unmitigated scenario because you have data of ICU beds and hospitalized and beds in the hospital. You know what is the availability. This is the horizontal dotted line. You see the unmitigated scenario, you go up of this by far. Also with the leaf scenario, you are above this limit, and only when you go to this LED that is testing and tracing, assuming that you detect 50% of the symptomatics and trace 40% of the contacts, you see that you are below the ICU capacity in this case. This 30% here is what is estimated to be normally available in normal conditions. Normally, you don't have the whole ICU beds at your disposal. Normally, you have only a number of them, and it's estimated that around 30% is available at ICU units in the hospital at any given time. So still, it goes a little bit about what is normal, but it's very small, or it's like half the number of available beds in the hospital. And this is just to check how many people will imply to be in isolation under this condition, of course. And you see that when you do 40% of tracing, for example, the peak, the maximum number of people that you will have in quarantine at any given time is around 9%. So it's something that is achievable in the sense that this is better than having the 90% of the population let's say in isolation. So I think this was my last slide, and just want to thank you very much, the organizers and my collaborators in this work. Sorry if I took a little bit longer than what I was given.
Thank you very much, Yamir. So, and Andrea Crisanti as well. And maybe now we are ready for questions. I see no question in the chat, so I encourage, if you have a question, please write it down. And meanwhile, maybe we can ask a few questions. Okay, I can start with a question for Yamir. And so the question is, now we hear a lot about cluster transmission in the news or something. So that essentially the idea is that most people don't transfer the disease very much, but disease occurs in bursts, like that one guy infects a lot, no? And when he meets many people, no? And this is what really drives the disease. Do you have something like this in your model? So can you see it in your model?
Yeah, in principle, it's something that you can see. In our case, as we were studying the condition, it was under lockdown, there was not too much mobility in that period. But we have some data about New York that was also in lockdown, but we have the temporal data, because in this work, one caveat that you can say is, okay, you took the static matrix and then you simply, what we did was, okay, this is the matrix, the contacts, the number of contacts, the interactions that I had when the disease started, and I just remove the interactions that takes place in the places that I know are closed, are closed now. So this is something that I do. But another thing that you can do is, okay, if I we're able to collect data daily or weekly about the interactions in each of these places, that would be a kind of temporal network that I can also use to do my model. And this is what we are now doing for New York. Actually, with those kind of data, you can explore these super contagion events. And actually, you can check that it's like you said, there are some places like 20% of the infection, the rule of 20/80. So 20% of infection take place in some locations that produce the 80% of newly infected individuals. And this is something that you can see also from the data.
Okay. There is another question to Yamir as well, is Matteo Gignani. What's the impact on social media or traditional media on changes in human behavior? E.g., wearing mask influences the parameter of the spreading dynamics and partially the interaction network, but the good behavior may be influenced by how people are exposed to information.
Yeah, of course. This is really, really important. Actually, now that we are coming back to this new normality, this is more important because, as I said, whether you go or not to a place and whether you not adopt a mass usage or not depends a lot on your decision and whether you are influenced by one side of the history or the other side. And this is very, very difficult to get into the models because everyone have their own opinion about whether they should adhere or not to these sort of things. And also depends a lot on the society. It's not the same if you study this in Europe or if you study this in the US. They have completely different notions of what is the freedom, let's say, or whether it should prevail the individual over the collective. In this case, I believe that it's a very important aspect that we don't have still all the tools to include in our disease modeling. Essentially, we know more or less how to model it or how to approach the problem. And these are two systems that are coupled and they have similar dynamics, but we still don't know how to model the feedback of one system into the other. Is something that is not completely included in the model, and it's also very hard to measure.
I can imagine. I have a question, since we are waiting other question. I have a question to Andrea Crisanti. Andrea, you are muted.
Yeah, okay, I can unmute myself.
That's my curiosity. What do you think about memory? So, I mean, I don't see you. Because I read a lot of papers, not always very, quite confusing. So what about memory due by coronavirus? Do you have data or?
No, this is something that we haven't studied in detail. You should look at memory T cells and the number and the ability to be boosted. There are very few studies on this topic. There is a recent study that shows that people that develop milder symptoms, they tend to make more T cell and memory cell, but I think this is only a very limited number of individuals. We have the impression, actually, it's more than impression, we can now demonstrate that the antibody level is not lasting. And it usually also the specificity of the antibody changes because you tend to make antibody against the S1 and S2 protein later on than the N, and they tend to last shorter time. So I don't know if this will have an impact on vaccine, but our impression is that the antibody don't last that long. And particularly in minor infection, they tend to disappear after 3 months.
Nobody knows why, of course.
And actually, the interesting thing is that there is not a correlation between antibody level and disease outcome. actually is the contrary. People who develop a severe disease, they tend to make more antibody at the hand.
Okay. This is because overreaction, immuno overreaction.
But can I?
Andrea, your camera is switched off.
I can switch it on, yes.
Yeah, Professor, just one question, because this is also have some impact for modeling. So when you say that it doesn't last, it doesn't mean that you lose immunity, right?
No, it has an impact only on the antibody level.
Okay, okay.
We are not saying that they are not, they have lost immunity. We're just saying that we see that the antibody level decrease significantly after 3 months. Whether this is a consequence on their immune status, we don't know.
Mm-hmm. Okay, thank you.
Anyway, I was impressed by Yamir model because you have 13, if I count well, 13 parameters in your model. A lot.
Yeah.
But I'm wondering, you have asymptomatic, that cannot become pre-symptomatic. Is correct? I don't know if it is real. How you can know if Andrea knows something? So, do we know something about this? An asymptomatic can become pre-symptomatic?
Well, you cannot distinguish between asymptomatic and pre-symptomatic. By definition, a pre-symptomatic is at that point an asymptomatic person.
Yeah.
It changes status at the time he or she develops symptoms. So I think the only way to model this is to start with with an asymptomatic person that either becomes asymptomatic or that either stays asymptomatic or becomes symptomatic. And only at that point, you can reclassify those individuals. And actually, there is no way to do this in a prospectively. You really need, the only way to do is to interview each individuals. You may make assumption that maybe the pre-symptomatic represent 15% of all individual that test positive for swab.
Yeah, actually, it's just a matter of where you take the branch of the two. In our case, pre-symptomatic is simple state in which you are asymptomatic, but you are in route to become symptomatic.
Exactly. Well, I tend to agree with you, Yamir. I mean, unfortunately, sometimes we made this distinction because the referee wants to see the impact in the modeling of the pre-symptomatic and their contribution in transmission.
Yeah, I agree.
The idea is that maybe the pre-symptomatic transmit more than those that remain asymptomatic, but this seems not to be the case.
Mm-hmm.
I think the distinction between pre-symptomatic and asymptomatic has to do with their contribution in disease transmission more than anything else.
Mm-hmm.
Yeah.
There are many questions now. I will read. This question is for both of you. What do you believe to be the best surveillance diagnostic strategy during the lockdown regime with bounding constraints on the number of swabs, the one that maximize the epistemic and public health value per swab? Is Piero Monticone.
Well, maybe I can say something on this because maybe I can draw from our own experience. Just after Bo, we advocate a complete change in the strategy to address the epidemic, and we propose that what we call active surveillance, that for every symptomatic individual that comes to the attention that we made diagnosis, we test all the layer of contact that has been very nicely described by Yamir. So in principle, we test the family, we test the neighborhood, and we test all the of the people that work with this person. So in principle, we go through these 3 layers of interaction and we test everybody. So it's not really mass testing, but it's a focus testing around these layers of interaction. And this actually worked quite well in our experience. We were able to stop the increase of the transmission in Veneto. And actually, this is what is currently done in Italy. For every positive individual, we test everybody in this network of interaction. We test friends, family, contact, and we test every person that works with a positive contact, with a positive case.
Yeah, alternatively, I think this is the way to go in practice, but alternatively, if you don't have enough resources, one thing that you can do is to impose isolation or quarantine to those that were in
this is an
touch with
alternative.
that. So
absolutely, yeah.
This is
which is a little bit more difficult if, for example, if you have a company and you want to make it, you want to keep it running.
Yeah. Yeah, but this is essentially what the Chinese did also. So they have these different levels, you know, green, yellow, and red, and then you are green unless you get in touch with someone that was tested positive, and then you have to isolate yourself until you get tested. So in our models, this 20–40% of contact tracing assume that you test the nearest people to you first, but then if you need more to get to that level of 20–40% of tracing, then you take it at random, then you isolate them without testing. So just say, okay, you have to remain there until 14 days, so 2 weeks, and that's it.
There is a question for Andrea Crisanti concerning the VOS study. Can you also comment about infected who never develop specific antibodies? Is Giancarlo Ferrera?
Well, we don't know why some people do not develop antibody, and we also do know why, for example, children that are exposed for sure to the disease, they do not develop antibody, they do not develop a disease. There is definitely another mechanism of resistance that probably doesn't have to do with adaptive immunity, but probably involves a natural immunity, which we still do not understand very well.
Mm-hmm. Yeah, thank you. And then there is José Betancourt. Question for Professor Moreno. What do you believe could be an alternative to contact tracing in countries where implementation is not very viable?
Contact tracing, you know, could be manual or digital contact tracing. So we were talking about manual contact tracing in the sense that we were taking into account that you normally need like a couple of days if you are efficient to contact trace this amount of people. But there have been some study that says that if you that the best combination is to have both. So if you can do a mix of manual contact tracing plus digital contact tracing, that will give better results than doing any of the two alone. So I will say that contact tracing is important. So you have to try to do that because in absence of immunity, the only way that you have to reduce the incidence of the disease is to cut down the transmission chain. And to cut down the transmission chain, you have to identify the source. These are the symptomatic or asymptomatic, the people that you test, and the contacts of the source that could have been exposed. So there is no alternative actually to contact tracing. You have to do contact tracing. The other thing that you can do, okay, reduce transmissibility, etc., but this is also something that you should do anyway. So, but I will say that there is no alternative to contact tracing. You have different ways to do contact tracing, but you should aim to do contact tracing.
There's another question, again, about the model. Tracing thresholds enter and play an important role in lowering the peak. is there an effective way to estimate what is the real value of this parameter, even considering the overall low diffusion of contact tracing apps? So how much contact tracing are we doing now? So that's a bit the question.
Well, actually, we are not doing too much, at least in Spain. I have some data in Spain. At least in Spain, there is no, I mean, the level of efficiency of contact tracing is around that 20%, but is widely spread across communities. It also depends a lot on the level, incidence level, because I mean, what we were supposing our model is that you have these 2 months of lockdown, and then immediately when you open, you have contact tracing already in place. You start to contact trace people. But if you wait to have an incidence like the one that we have in Spain now, that is 8,000 new cases in Spain, then there is no way you can do manual contact tracing with 10,000 new cases every day. There is a paper that came out like 2 days ago by Marcel Salaté that they were analyzing the results of the implementation of the app in Switzerland. I think that they were already getting some nice results with only 20% of adoption rate, which is really, I mean, 20% of adoption rate is not that much, because you have to think that in order to trace a contact, both ends of the interaction have to have the apps. Otherwise, you cannot trace the contact. So if you have, so in an homogeneous population, if you have a 20% of adoption, that means that you can only trace 4% of the contacts. So this is really, really small number. So, but anyway, it's something that you add. It's not something that is, I mean, something is more than nothing in this sense. What we did with the study in Boston regarding the 20, 40% and the tracing was referred to the capacity that was at that time in the city of Boston. So you always have to calculate these SIMs as a function of what is the incidence that you have when you start doing the contact tracing, and what is your capacity to do both test and tracing. Depending on that, then you can set your objective, your goal. So, but there is no given threshold. It depends on a lot of variables. It depends on the incidence, it depends on how many people you test, and etc.
The last. No, I think we can. We don't have any other question, but I will ask a last comments for both of you. So the autumn is very close. So it's close. What will happen after your seminars? It's quite clear to me what to do. No, actually, what we should do as country, but what will happen?
Well, maybe I can say something. I think. We should dramatically invest in our testing capability. And as Yamir has said, we need, as additional tool to have an effective contact tracing, either manual or digital. I think these are the 2 areas where we need to invest, because this information will also feed a model and will allow us really to refine better and better strategies.
Yeah, I fully agree. This is the only thing that you can do. The vaccine is not expected anywhere soon, anytime soon, or at least not in the next, for the fall, not for sure. And then even if you have the vaccine, you need time to produce and distribute it, etc. So it's not something that you will have in the next few months. So you have to resort on traditional methods. It's identifying the transmission change and trying to cut down the transmission change. So this is test and trace, nothing else.
I hope we are doing it. I hope. I hope so. So please help. Andrea, you are in Italy, so, and Yamir, I don't know if Spain is doing in this, is working in this direction. I have no idea, but Italy, I don't know. I'm reading a newspaper. Anyway, I want to really, we want really to thank you so much. It was very, very, very nice, this discussion talks. I really enjoy, at least I think all of us. And thank you to all the people that, stay with us till now. this date. And okay, I cross fingers. And
then the next seminar of the series, we have another two seminars, 23 of September.
Yes. And again, a COVID. There will be, we'll go in another, other colleagues from users.
From Brazil,
from
actually.
Brazil,
so we'll see maybe another perspective from Brazil. And then there is another seminar on deep learning for melanoma, so different subject. Yeah. And then we'll go on roughly every 2 weeks. So we have already a schedule. We'll send details on Twitter and on the website.
Okay.
Thank you very much.
Thank you very much.
Thank you very much for the invitation.
Bye now. Thanks a lot.